Okay, the first two equations for SUVAT actually come from the velocity time graph. This is a description of a particle that's under constant acceleration, and we saw in the graphing section that we have two quantities we can get from a VT graph. We can either get the displacement, which is the area, or we can get the acceleration, which is the gradient of the line. Under constant acceleration, the gradient of the line will be a straight line. So we can draw our equations. Let's go for S. S is the area under the curve. So you might have UT and then the triangle on top. We need to add the height here is V minus U. So remember that's V minus U across that line. So it's 1/2 V minus U times T. When we look at the equation, we're going to have UT minus 1/2 UT, which gives us 1/2 UT left over. So we've got 1/2 UT plus 1/2 VT, which is 1/2 U plus V, all times T. Or you may actually recognise that it's a trapezium, and the area of a trapezium comes from A, B, and the perpendicular height between them. And now, if we butt these up, we've got height U. We would relabel that as U, V, and T, and that would lead us to S equals 1/2 U plus V, and H is T. So we've got the equation two ways, one from doing two separate sections, and the second one from the area of a trapezium. The second equation comes from finding the gradient of the line. So A is the change in velocity over the change in time. Change in velocity is V minus U again divided by T, and that's our standard formula. A equals V minus U over T, and this one is often rearranged in a number of different forms. We can multiply by T, so AT equals V and U plus AT, or often we might need U equals V minus AT, and one useful one is T is the change in velocity divided by the acceleration required to do it. These two you could rearrange a little bit, and you can get T is equal to 2S divided by U plus V, which is actually saying half of the average velocity, S divided average velocity is T, and you might remember that from science. They use that symbol, trial S is VT, and if you want T, you've got V over S. T? Sorry, V and S. See, we don't use these formally, triangles. So V, if we wanted to get T, displacement over the average speed being covered, U plus V divided by T. Right, so that's the first two equations. They get used in a number of fairly simple ways to calculate the basic things like we were doing from the graph yesterday. So the example they give is car. It is useful to draw diagrams. They don't have to be truly a description. So a car starts from rest, so the starting velocity is 0 when T equals 0. 30 seconds later it's past the speed trap, so T equals 30. We've now got a car that's moving velocity of 30 meters per second. Oh, 45 kilometers an hour, sorry. Need to convert that into our units, so to convert this to velocity in meters per second, you can take 45, and that's kilometers over hours. If I change the kilometers into meters, I want to divide by 1 kilometer is 1,000 meters. Change hours into seconds is I would like to multiply by 1 hour, which is 60 minutes, and multiply 1 minute by 60 seconds. This is a little way of using simple facts to build up. So I'm just following the chain of cancellation. The K cancels to give me meters on the top, H cancel to give me minutes on the bottom, minutes cancel to give me seconds on the bottom. So I've now got meters per second. Okay, so that's a little tip for you when you're cancelling. So cancel the K's and then cancel the minutes. Also minutes, I'll just cancel 1 meter. Meter, so that was correct, left meters. Cancel the hours and cancel the minutes. And what we're left with is meters per second. And that gives me a conversion. 60 seconds. Divide by 3.6 effectively gives me 12.5 meters per second. So that's a converted unit. Questions they'd like to know is what's the acceleration? So acceleration is normally shown on a diagram with 2 arrows on the head. And they'd also like to know how far did we travel in this time? Yes. So I'm going to try and treat it using 2 different formulae. Use our 2 formulae to calculate the acceleration. A equals the change in velocity, so we've got 12.5 minus the initial velocity, the u, is 0, divided by 30 seconds. So my acceleration is now 5/12. So multiply that by 225 over 60. 25 over 60 is 5 seconds, 12 meter per second squared. And if I want to do the distance covered, we've got the S equals a half U plus V times T. It simplifies down to 15 times 30. And they say it's 187.5 meters covered in that time. And so that's using both those formulae. We're going to use the other forms to find some other equations. So there are some other equations that we can find. So the other equations we can find come from using these to substitute into each other. So we'll take our first one, which is based upon my black notes. If we start with S equals 1/2 U plus V times T, and we got V equals U plus A T. What we can do is we can actually rearrange this one to give me my time-based equation. So T equals V minus U, transfer that over and then divide by A. And then we can substitute that in, because all these variables must be talking about the same situation. So if we then substitute it into the equation, yes, equals 1/2 u plus v times v minus u divided by a. Notice at the top is difference of two squares, so we get u squared minus v squared minus u squared over 2a is equal to s. And this often gets rearranged into the form where the final velocity is being calculated as a square. So we've got 2as equals v squared, and carry the u to the other side. And we've got u squared as. V squared equals u squared, add on 2as. So this one, what we need to think about is when we've got the variables, it's often useful to think about what sort of variables have we got. So it's like do that, and you tick off when you go into a question which bits have you got, and it helps you choose which equation do you need. We can also put the acceleration put the v straight into this equation. The other one is to put the equation straight in. So this is equation 3. Equation 2. Equation 1. Equation 2. Equation 3 and equation 4 is if we've replaced this v, that expression. So take those 2. So we get s equals 1/2 u plus at times t gives us 1/2 of 2u, add on at squared. These twos are cancelling, so it actually leads to our equation s equals ut, add on 1/2 at squared. And you can do another version where you've rearranged that to say u equals v minus at and substitute it into the same equation. So we've got s equals 1/2 v minus at, add on v t, and that gives us 1/2 of v squared, 2vt minus at squared, so we get a vt minus 1/2 at squared. That last one I don't often rate, I don't often use it, but there's the 4 main equations. I'm only going to call that an adjustment to the first one. So let's put in another version of the equations then. Here's another example, again straight from the book. This is their example 10. It says particle P. Now, particle normally means it's small, i.e. no size. We're not talking about a rolling particle, a rolling item. They also mean that generally particles, unless they mention friction, there is no friction, no air resistance to them. From air. We'll do particles on a slope, and they do sometimes have masses later. So it's not rolling, no friction from the air, and its size. So no sizes, there's no worries about what's happening. So it says the particle is moving on the x-axis with constant deceleration. So it's moving in that direction. It's got an acceleration going the other way of 2.5 meters per second squared. At time t, the particle p passes through the origin, so we're at origin here, moving in the x direction with a velocity of 15. First part it would like to find is the time between that point when it goes through O and when it returns. So we want to find when the displacement, so this goes off, it slows up, and then after some distance it starts coming back. Now this is actually parabolic because we've got a constant acceleration. If we didn't have constant acceleration, we wouldn't be able to solve this straight away with the equations. So what actually this means is when we're coming back this way, v equals negative 15 meters per second at this point. We don't need to know that, but that's the implication of what they're saying under constant acceleration. Sometime later we come back to t equals 0, O, when t equals 0. And we also would like to know when else do we come back through this equation. Okay, so when does that t happen? So the thing we know is the displacement. So let's do our little SUVAT list. SUVAT. We want to know the time. We know the displacement, it is 0. We know initial velocity, that's 15. We actually do know this is minus 15, but it's not something we're given in the question. But we know that from symmetries of the quadratic that's needed, because if this keeps doing the same thing. And the acceleration we know, and that is, notice it's going in the opposite direction. So we're going to say this is positive x, and that acceleration is negative, so we need to put that in, minus 2.5. So that's all the information we need know. To find this time, well, I need to know, do I have s? Yes. Do I have u? Yes. Do I have a t? That's what I want to work out. Do I have a half? Yeah, I know what a half is. I know what a is. I know t. So I can use this equation, which is what we're going to do. So we put them in. We want to know when 0 equals 15t plus 1/2 times 2.5 t squared. And that's a negative. Simple quadratic, and we can factor out a t. 15 minus 1.25t. And that means we can now calculate the first value, t equals 0, we knew. That's the time I'm now setting up here. That's when it's going that way at 15 meters per second. When we say that 0 equals 15 minus 1.25t, so t equals 15 over 1.25, that's going to be 544, that's going to be 12, at 12 seconds. This is the other time, and this is when the particle's now going that way at 15 meters per second. So this one was the original time, and that was when the particle was going right from past the point O. This second one is when the particle's coming back the other way at the same velocity. If you want to check it, we can actually put it into the earlier equation that we derived, the v squared equals u squared add on 2as. Oh no, we need that one in a minute because we need to work out the distance. Do they assume? We might follow it up in a moment. Part 2 of the question is to find out how far did we go this way. That's part 2. So in this part 2, let's do the SUVAT table again. S, U, V, A, T. We want to know the displacement. U we know was a positive 15 meters per second. V, when we get to this point, maximum distance, it's no longer moving either direction, so V is 0 meters per second. My acceleration, still negative at 2.5 meters per second squared. T, we know nothing about T, although we could probably assume it's going to be 6. It's halfway through the journey, but we're not assuming that. It's like this minus 15 here. I didn't assume that's what's happening, although it is. So we've got equation using U, V, A, and S. Look at our equations, and number 3 has V, U, A, S. So we're going to use that version of the equation. V squared, U squared, plus 2AS. And this was S equals UT plus a half AT squared. These equations are not given to you in the book. You do need to know them. So put the values in. 0 squared equals 15 squared. Add on 2 times minus 2.5 times S. 15 squared, 225. So 5S equals 225. S equals 225 divided by 5. And that is 45 meters. Yep. So that's the distance on the journey out. The total distance covered. So that's from to our point X. So our distance there is OX. They want to return, so distance covered is twice that. Meters. They called it A, not X. Okay. If you want to quickly check, what we can do is find out from let's just do. We know the return journey is now this. Starting velocity. So if we take the return, V squared equals U is now 0 because we're at X, 0 squared. Add on 2 times minus 2.5. We know the distance is 45. So this multiplies to give me U squared add on 2AS. Yeah, we got that problem with the signs. 2.5, yeah, is negative 225. Now there's a little quirk in this because of doing the square root. When we do the square root of this, we have a complex number. Square root of 225 and a value I, which gives us 15, and the I is what indicates that we're going in a negative direction. We've got this change about speed. The way you would normally deal with that if it was appearing is possibly redefine your direction X. So you're accelerating towards the answer, the O again. But this is how I can show that this statement was true. Okay, that's the end of that video.